Okay, so this is chapter 2, problem 23. So the problem asks us to find the integral of a dot ds over a hemispherical region that's the top half of a sphere with a radius of 3, centered at the origin with a flat base on the xy plane. So here's our xy plane, here's the flat base of our sphere, and if our radius is equal to 3 for a sphere, that means that the radius is equal to 3 all the way around in this direction and all the way around in this direction. So if you look at the problem, for part A, it's actually asking us to find the left-hand side of the divergence theorem. You can kind of see over here, the left-hand side. And then for part B, this del operator dot A, it's actually asking us to find a piece of the right-hand side. And then when it says verify the divergence theorem, we're going to find the rest of this right-hand side by integrating over the bounds and multiplying by dv. And we should expect that the answer that we find in part A is going to be equal to this this del operator dot a multiplied by dv and integrated over the volume. So when it says verify the divergence theorem, we want to find the left side and then the right side and prove that they're equal. So that's what we're going to do for this problem. Okay, so we're going to start with the left side here. And the first thing that we need to do is set up our ds values. So when we're setting up ds, first we need to ask ourselves, so okay, what are our surfaces? And what are the normal vectors to those surfaces? So we have two surfaces in this problem. So the first surface, well, maybe I should leave that drawn there. The first surface is this, the top part of the sphere that you see here. So the sphere sitting on the plane. So this guy, just the spherical volume. And the second surface is this flat circle inside of our sphere here. So that's surface number 2. So these two surfaces are going to have different normal vectors. And so the normal vector is so that we can find the flux flowing through that surface. And we need to find the vector that's at a right angle to that surface. So first, if you look over here, I kind of have them pre-written out, but I'll show you how to find them. There's a cheat sheet kind of down below. So for the bowl, the upside down bowl part, our normal vector is going to be in the r hat direction. And the r hat direction is actually radial, so it just means that the vector direction of our radius pointing all the way around the shape. If you think about a circle, the radius goes all the way around the circle. The r hat direction is the same, and it's just pointing out by convention. So out of a circle is the positive r hat direction. So, okay, so we know that that's going to be our normal direction, so let's find our ds. So spherical, right, because we have a half sphere, and we need an r hat direction for the surface. So if we scroll down, let's look at this sheet here. So spherical, and we're looking for an r hat direction for the surface. So we can refer to this guy right here. So this is giving us a differential surface. So basically the outside surface area of a sphere, that's going to be in the r hat direction with an r hat normal vector to it. Okay, so that's what we're using for the, oops, sorry, I've got a lot of stuff on the page here. I already did problem 2 before this, so, or part C before this. So that's the first surface. So ds for the spherical surface. Now ds for a flat circle. So we're actually going to take this from the cylindrical coordinate system, because if you think about the cylindrical coordinate system, the tops and bottoms of the cylinder are circles. So the flat circle in the cylindrical coordinate system in the z hat direction, that will be the differential surface for a flat circle. Okay, so looking at this, we can actually use the z hat direction for this, this piece here, even though these two pieces kind of won't be in the same coordinate system, but the math will work out. It's going to be okay. So we're looking for, so negative z hat is going to be out of this surface, right? Because this is our shape, and so out of the shape is going down. So we need a negative z hat for a flat circle. So we're going to look at the z hat direction for the cylindrical coordinate system. So I kind of pre-wrote it over here. So let's go down here. So looking at our cylindrical coordinate system in our z hat, we have this r dr d phi, and that is what we use for our problem here, right? R dr d phi and the negative z hat. So just kind of a little bit of a side note on how to find those. Okay, so what we're going to do now is we're going to take our a vector given to us by the problem, okay, and then our ds's, and we're going to solve first a dot ds for surface 1, which is the bottom circle, and then we're going to solve this a dot ds for surface 2, which is this top bowl piece, okay? So let's go ahead and set that up. Okay, so first, for this guy here, so we have our A, right? We're going to dot it with our ds. It's going to copy paste kind of for ease here. So that's our A and our ds, so our A, ds, right? And we don't know what our bounds are yet. We haven't looked at those yet, so we're going to, I'm going to close this guy for a second. So we're going to just write S naught here, which just means like the, eventually is going to be our surface here. Okay, so we know that if we dot, so z hat dot z hat is equal to 1. These directional unit vectors, when you dot them with each other, it's equal to 1. So if we dot z with something that would be perpendicular, like y hat, it would be equal to 0. But dotting it with itself is going to give us 1. It's just the magnitude of this directional unit vector squared, and the magnitude of these directional unit vectors is equal to 1. So just an aside, remember that kind of from just the first intro section on vectors, but we'll see that a couple of times. Okay. Okay, so we're going to simplify here. We're going to take out that z hat dot z hat equals 1, and we have r dr dv left here. Okay, so let's go ahead and break up things in terms of the differential pieces that we have. We have a dr and we have a d phi. Okay, so let's pull out, we don't have a dz though, we have that z piece, so let's pull z out to the outside because we can treat it like a constant, and we just need to know what is z, where our shape is, right? Z isn't changing, it's a fixed value wherever our shape is. So we're going to have to look at what it is by examining our shape. D phi. Okay, so now let's look at what our bounds are. So we're looking at this flat circle piece first. So we need the bounds for r, for our flat circle, okay? And then we need the bounds for phi, and then we need to look at what z is. Okay, so for a flat circle, our bounds for r, 0 to 3, right, for our flat circle. Let's go ahead and put those in. So 0 to 3, and then our bounds for phi. So by convention, phi starts here, kind of in this x hat direction, positive x hat, and it goes all the way around in this angle direction. So phi is going to go from 0 to 2 pi. It's going to make a full rotation of 360 degrees. So our range for that phi is going to be 0 to 2 pi. Okay, now last but not least, what is our z equal to here? Well, our circle is on the xy plane, right? So what is z while we're on this plane? Well, z is actually equal to 0, right? There's no change in z. This is just kind of a flat circle at z equals 0. And so because we have z in our equation, due to like what our a vector was when we started out with, it's actually going to set this whole thing to 0. We'll go ahead and solve out the rest of the pieces here, though, just so you can kind of see what the rest of the math would work out to when we solve our integral. But so r squared over 2 from 0 to 3, phi from 0 to 2 pi, and then multiply by 0 because our z is equal to 0. So this whole first piece is equal to 0. So if you realize that right away, you could neglect doing this piece and just kind of say that surface is equal to 0. But I think it's important to kind of solve these out and understand how to set up these pieces for when they don't equal 0. Okay, so our second piece here, we're doing this bowl. So we have kind of an issue here where this A is not in the right coordinate system for our ds and for our spherical surface. So we need to convert A to our spherical coordinate system to be able to manipulate the vector with our ds, or you just need to know what this z hat dot r is. You could do that as well, but we're going to kind of do it this way instead. So I kind of copied a little snippet from the cheat sheet and put it up here. Again, if you look in the description of this video, you can click and you can go ahead and look at this guy, and you can see the cheat sheet for yourself. But I kind of pre-copied this out here. So we have z in the z hat direction, so it's a pretty simple conversion. So we have z, so we're going to take the magnitude of z, which is equal to r cosine of phi, or cosine of theta, I'm sorry, and then we're going to take z hat, which is equal to cosine of theta in the r hat direction minus sine of theta in the phi hat direction. So I just forgot a little phi hat there. So we're going to take this, okay, copy, and we're going to go down and we're going to convert our A here, okay? So I am going to end up with r cosine of theta multiplied by cosine of theta r hat minus sine of theta in the phi hat direction. Okay, now we have our A, right? We've found our A and we have our ds. They're in the same coordinate system. So now let's do A dot ds. Okay. Just before we do our dot products, I think it helps to put everything in the same coordinate system. If you want to approach it in a different way, I feel like that makes the math way more complicated, but feel free to each their own. There are multiple ways that you can go about this, so I won't fault you for that. Okay, so we're dotting these two together, right? Okay, so now let's see what our vector components are, because some things are going to cancel here. So phi hat dot r hat, right? Well, these guys are perpendicular. We can tell that by looking at our shape, right? So this phi hat, right, and this r hat, these guys are perpendicular to each other. If we dot two vectors that are perpendicular, well, that's going to give us 0. This r hat dot r hat, for the same reasons we said above, for z hat, is going to equal 1, because it is a directional unit vector. So we're going to be able to get rid of this piece right here. And now let's go ahead and simplify our math. So we have this, so we have this r on the outside times r squared first. So r, oops, sorry, I forgot to switch my pen back. So r to the third, right? And then maybe actually I'll keep the pieces kind of separate before I start simplifying here. So r cosine of theta, right? And then we have cosine of theta times r squared sine of theta d. Oh, we have sorry. Let me be a little more careful here. R cosine of theta times cosine of theta still, right? Cosine of theta. And then that whole piece, because we just didn't simplify that first part right away, right? R squared sine of theta d b. And if anything that I'm doing is kind of hard to follow, if you pull up again in the link in the description, just sort of the problem, because I know not everything is in the frame as I'm doing this, it might help kind of follow my work a little more. So, okay, so now we need to set up our integral here and kind of combine our terms. Just kind of checking to make sure we're in the right direction here. Yep, okay, so let's simplify a little more. So we have r cosine squared theta, r squared sine. I'm just kind of doing this piece by piece. I know we could do a lot more, but I just kind of want to make sure that every step that I'm doing here is okay to follow. Actually, I'm not going to copy it. Okay, so let's combine those r squared terms, or r terms, and pull them to the outside, because we don't have a differential r. We just have this differential theta and this differential phi. So we're going to treat our r as a constant here, which means that for the piece that we're looking at, there is no change in r. Sine of theta d phi. Okay, so now let's break up our differential terms here. So we have this d theta and d phi. So let's go ahead and break those up. So we have cosine squared of theta d theta, and then cosine squared sine of theta d theta, sine of theta d theta, and then we have d phi. Okay, so we need to look at our bounds here for both of these guys. So what is our bound for theta, and what are our bounds for phi? Okay, so let's scroll up here. All right, so our theta, so by convention, you won't really see this in this problem, but by convention, even for a full sphere, theta only goes from 0 to pi. In this case, so by convention it starts here at 0 and then it goes to pi. The reason why we don't go a full revolution is because it would actually double your surface area or your volume. But just for this problem, so 0 to pi, or pi over 2, sorry. So 0 to pi over 2 is going to be 90 degrees. Okay, so now let's look at our phi here. So for our shape, for our phi, we're going from 0 to 2 pi. So starting here at 0 and then a 1 full revolution to 2 pi. Okay, so let's go ahead and plug those in. So 0 to 2 pi and 0 to pi over 2. Okay, so now things look a little dicey here. Oh, I think I might have run out of writing a little big, aren't I? Okay, let's see if I can fit this in the space. Okay, so let's solve for our phi piece first because that'll be pretty easy. Okay, so equals r to the third, and then just integrating for this d phi, we're just going to end up with phi from 0 to 2 pi, 0 to 2 pi, and then we still have this integral from 0 to pi over 2. So this is actually going to require a u sub to do this guy. Cosine squared theta, sine of theta, d theta. Okay, so the u sub isn't too bad. So u, we're going to take, if you have cosine multiplied by theta or anything like that for an integral, notice that the derivative of one is actually equal to the other. So it kind of gives you, it makes our integral a little bit easier to solve. It's actually kind of necessary to solve integrals like this. So negative sine of theta. So say if you have sine squared cosine, or sine squared theta multiplied by cosine, you could kind of do the same thing. I'll kind of take you guys step by step through this guy. Okay, so negative du equals sine of theta. So we're going to do a substitution here. So we're going to sub in our u for cosine of theta, and then we're going to sub in our negative du for our, sine of theta d theta, because we took the derivative. So we're going to sub in our negative du for sine of theta d theta. So our integral is going to look like 0 to pi over 2, and then we're going to have u squared, right, because we had cosine squared, and then we're going to have a negative du. So subbing that just in for sine of theta d theta. Okay, so now the last thing that we need to do here is we actually need to change our bounds. So because our bounds were for theta, we need to change them to be for u. So it's actually going to be cosine of pi over 2 for our top bound, and then cosine of 0 for our bottom bound. Cosine of 0. So our bound change here is actually going to be from 0 to 1 on the top. So it's going to be from 0 to 1. So when we integrate this, we're going to get negative u to the, well, actually, I'll not skip, u squared du. And then we're going to end up with negative u to the third over 3. My pen's a little thick here, especially because I'm running out of space. Third over 3 from 0 to 1. So it's going to be 0 minus a negative 1 to the third over 3. It's 1/3. Oh, sorry. 1/3 for this piece here. Okay, so we're going to take that 1/3, and then we are still multiplying it by this first piece that we have all the way over there, right, before we solve just that last chunk of the integral. Hopefully you guys are following this. I'll clean up my notes a little bit so it's a little less messy. Okay, and then we have r to the third times 2 pi minus 0 times 1/3. Because we just solved the piece separately. Okay, so last question. My background noise is like killing me right now. Last question is, what is r here? Well, r is constant, right, for our bowl here. R is a constant value at all points of the surface, because r is equal to 3 all the way on the top portion here. R here is equal to 3, equal to 3 here, equal to 3 here. and r is equal to 3 all the way around the rim. So at all points on the surface, r is equal to 3. So we can go ahead and plug that in for our final answer. And we're going to end up with 3 to the third times 2 pi times 1/3, and that's going to be equal to 18 pi. Okay, and we found our first side. So now our goal is to solve the right side here, so the other side of the divergence theorem, and also prove that that's equal to 18 pi. So I'm going to stop that video and then let's go ahead and move on to part B and C.